Today what we are going to study is that about the pushdown automata. Okay, so before that I'll give you just a small intro. So already we have studied about the regular languages, right? For regular languages we have the finite state machines. That is, we have studied about the deterministic finite automata as well as non-deterministic finite automata, and also we have studied about regular expression. So these are all some ways of expressing your regular languages. Okay, and also we have seen about the regular grammar for this also. Okay, we have studied about the regular grammar, and we have also seen the pumping lemma, so that we'll be able to know whether a particular language belongs to a regular language or not. Okay, so we have studied about pumping lemma, and then we have seen several properties and so on. Okay, then we have started with the context free languages. So while we were studying about the regular languages and this pumping lemma, we have seen that not all languages can be accepted by this regular language. Okay, so we have seen one such example, that is a power n b power n. Okay, a power n b power n. So this language states that when n is greater than or equal to 0. Okay, so it states that the n is not fixed, and it says that the number of a's should be equal to number of b's, and b should be preceded by the first b should be preceded by all a's. Okay, and since this kind of thing cannot be done using your finite state machines, because here a counting is required. Okay, you need to count whether the number of a's is equal to number of b's, and whether the b is preceded by all a's. Okay, so such kind of thing is not available in your finite state machine, because we don't have any memory. We have a finite memory which could not be helpful in reading counting this number. Okay, so then we go for the next hierarchy of language, that is the context free language. So in context free language we are having we have studied about the context free grammar, and so the machine that generates this context free language is that the push down automata. Okay, so like how we have DFA and NFA for regular language, we have here push down automata. So we are going to study about this push down automata in this class. Okay, so what is a push down automata? So here, as I said you, in DFA, we will be able to remember only a finite amount of information. That is, we don't use any explicit memory for that, and we'll be not. So we will not be able to remember certain informations, like how we have seen in that example. It is not possible to count the number of a's and number of b's, and whether it is followed by whether the b is followed by all a's. Okay, so it is not possible to do that. So we are going to use the memory, which is called as stack. So you know very well stack and what are all the operations we are doing using stack, right? So the stack is the memory that we are going to use here in this push down automata. Okay, so a push down automata is is an NFA epsilon, is an epsilon NFA with a stack. Okay, and the stack operation, as usual, the push and pop operations, we are going to use it here. So we will see how it, so why it is needed. Okay, so the same example, you can see that when 0 power n, 1 power n, when there is no definite number of n, okay, when n is just greater than or equal to 0 and you cannot define n, then it is not a regular language. Because if it is regular, okay, if suppose if that value is fixed, okay, so for some fixed value of k, for example n equal to 3, okay, then you will be able to draw a DFA or an NFA for it. See, for example, if k is equal to 3, then the language is limited. Okay, it is a finite language. It has very finite number of strings. Then you will be able to draw a DFA like this, right? So here also you can see equal number of zeros and ones, two zeros, two ones. But the thing is here the language is finite. And but when you take n is greater than or equal to 0 without any fixed value, then the language becomes infinite and you'll not be able to put it in a DFA. Okay, so that is why we are going to move it move towards the push down automata or the context free language. Okay, so the in this when we have infinite language, okay, when the language is infinite and when we have an infinite number of states, it is not possible to go with DFA. So we are going with this stack, infinite stack, so which will be able to solve such problems which could not be accommodated in this regular language. Okay, so we'll study some of the things. So the first we'll look into the formal definition of a PDA. Okay, the pushdown automata, we have 7 tuples. Okay, if you remember pushdown non-deterministic finite automata or a deterministic finite automata, I hope you remember that it is having only 5 tuples. Okay, we call it as quintuple. Okay, but whereas this pushdown automata, it is going to have a 7 tuple. So some of these things already you have studied in for finite automata. Okay, so Q already you know what is it, a finite set of states, and sigma already you know, finite input alphabet, and the new thing here is gamma. Okay, gamma. So gamma here, as we are going to use a stack memory, the stack alphabets is going to be present in this gamma. Okay, so the sigma, it will give you the finite input alphabet like A, B or 0, 1, whatever the inputs you are going to use, that will be present in sigma. And this gamma will be having the stack alphabet. So as we are going to use stack, what are all the inputs that you're going to use in this stack? That is called as the stack alphabet. Okay, and then Q naught. So this is the initial or the starting state, and so it is already in the capital Q. And another new thing that we are going to include here is Z. Okay, Z naught. So this Z naught is going to be the starting symbol of your stack. Okay, this is going to be the starting symbol of your stack. And then F, capital F, as you know, it is the set of final or the accepting states. And finally, we have the delta that represents the transition function. So already we have studied it for the NFA and DFA, the transition function. Okay. So how it is written for pushdown automata is that here we are going to have, so as you, if you remember in your DFA or an NFA, you will have 2 components on the left side. That is, you will be having Q, and for DFA, if you say it is only Q into sigma gives Q. Okay, and for NFA, if you remember, Q into sigma union lambda. Okay, so it can be either any input from sigma, or you can use lambda transition. As you know, for NFA, lambda transition is also possible. So this will give you 2 power Q. Okay, so that is, you have different possible options. So these are the transition functions for your DFA and NFA. Now for pushdown automata, as we are involving the stack also, we are going to have 3 components in your transition function. So how will you write your DFA or an NFA transition? You will be having something like delta of Q naught comma A is equal to Q2. Okay, so it means that from Q naught, if you read input symbol A, it goes to Q2. Okay, so here you have only 2 components. Whereas in the pushdown automata, we are going to have 3 components. One is the current input state, okay, the current state. And the second component is the input symbol, okay, the input symbol that you are going to read. So either it may be an input symbol from sigma, or it can be lambda or epsilon also. Okay, and the third component is the stack alphabet. Okay, the present or the current input symbol, or the top top of the stack. Okay, so that is also included in the left hand side of your transition function. So that will give you the finite subsets of q into gamma star. Okay, so when we see the example, you will understand that. Okay, so here it is explained each parts of the transition function. So Q, it means that it will consider the current state. Okay, like whether it is in state Q naught or Q2. Okay, like that. So it represents the current state. And second, and this gamma, it represents the top of the stack. Okay, so as you know, in stack we have only one opening, and any insertion or deletion, anything, okay, by pushing or popping, everything will be done on only one end, the top, right? So the top of the stack, only you will be able to access the element. So gamma, it contains the symbol on top of its stack. And sigma union lambda, okay, or epsilon. So the current input symbol, okay, either it may be the any input from the input alphabet or the epsilon transition also. Okay, so and on the right side, finite subsets. So it means that again this is a non-deterministic pushdown automata. Okay, so since this is non-deterministic pushdown, so you will have choices. Okay, so it is not necessary for a transition function we can have a definite output. Okay, it will go to this particular state Q2 or Q1. Okay, you may have choices, so that is why it is finite subsets. Okay, it has several options. And the Q, it specifies the new state, okay, to which state it is moving, the new state it representing. And gamma star, it represents zero or more stack symbols that will replace the top stack symbol. Okay, so as you are doing some transition, so what is the so how we are going to replace the stack with? Okay, so it may be zero or more stack symbols may be replaced instead of the top stack symbol, and it has to be done in a particular sequence. Okay, so that we will see while doing the example. So we have the transition, you can see like this. Okay, so Q is the current state, and A is the input symbol, and this is the stack symbol. Okay, so when you have a transition like this, okay, when you have the input like this, so you can have a finite subsets. Okay, finite subsets of or the different options you can have. Okay, so it means that it may go to either state P1, and so it can also be represented using such transition graph. So from state Q on reading A, and when the stack symbol is Z, you are moving to state P1, and this symbol, it represents what is the stack you are going to replace. Okay, how the stack symbol is replaced with. Okay, so if Z is replaced with gamma 1. Okay, or if you are going for this transition, okay, the top of the stack is replaced with gamma 2. Okay, so this is how the transition function looks like in a pushdown automata. Okay, and also as we have said, in the second component, it can be either sigma or it can be lambda also. Okay, so instead of this input alphabet, you can also have a lambda or an epsilon also. Okay, so the current state and the current input symbol, here there is no input, so it is lambda transition lambda, and currently top of the stack, whatever the symbol it may be, and it is moving to we have different options, either it may move to state P1 or to P2 or anything. Okay, and while doing this transition, what is the how the stack contents are getting changed. Okay, so the stack contents may get changed each time for each transition. Okay, so now we'll move on to an example. Do you understand this, ma, this definition part? Yes. Yes, do you understand the theory part, Ma, the definition part? Can I get some response? Yes. Yes, thank you, Osborne. So now we'll move on to a problem. We'll see how the non-deterministic push-down automata works. So let me give you a schematic representation of a pushdown automata. So we'll be having the input file like how we do it for the uh, finite uh, finite automata. We have an input file and we have a control unit, and we also have a storage. So we are going to use the stack as the storage. Okay. So what happens? The in each move, okay, in each move or in each transition of the control unit, in each transition or the each move, the control unit that is going to read one symbol, okay, one symbol at a time. So your inputs file is having partitions, each cell having one input symbol. So at one transition or at one move, only one symbol will be read. So one symbol will be read from the input file, and so at the same time, here in the stack also, the contents of the top of the stack will get changed. Okay, so in each move, the control unit will read from the input file one input symbol at a time, and also the top of the stack, the content of the top of the stack also gets changed. Okay, so each move this will happen. So that the change may happen through either through the push operation or through the pop operation. Okay, and then we'll be having, so how this push or pop operation will happen is that it is based on the input symbol that we are reading. Okay, so every move it is controlled by the or determined by what is present in the input as well as what is present in the top of the stack. Okay, so based on the content that you're going to read, okay, the input present input symbol that you're going to read, as well as currently what is the top of the stack we are having, based on that the transition or the move will be determined. And here so we are going to learn this push down automata as an acceptor. Okay, so this term already we have studied for deterministic finite automata as well as non-deterministic finite automata also. So here we are going to design a machine, okay, where we'll be given a language for which we are going to design a machine, okay, that is design a push down automata. And the language may consist of several strings, and you'll be having so many strings. So if the string is accepted by the pushdown automata, the pushdown automata should accept all the strings that are acceptable in that particular language. Okay, so if we give any other string apart from this language, then it should reject it. Okay, so the pushdown automata can act as an acceptors. Okay, and so we have already seen the definition part. So we'll now straight away go to the example. Let me give you an example so that you will understand how to construct a pushdown automata. Okay. So the same example let us take, which is L is equal to a power n, b power n, such that n is greater than or equal to 1. Okay, so already we have proved that this language is not a regular language by using the pumping lemma. Okay, so this language is not regular language. So now we have moved the hierarchy from one level to the next level, that is from regular language to the context free language. So now we will check whether this language can be accepted, whether it can be accepted by a push down automata, so that this language could be called as a context free language. Okay, so how will we design this push down automata? So now as we are going to use the stack as the memory, so now what is required of this particular language? This language requires that you should have the equal number of A's and B's, and that too the first B should be preceded by all A's. Okay, so we need to not only count the number of A's and B's, but also the position is also important in this. Okay, so now what is the logic we can use using the stack to make this language to design a push down automata for this language is that what we can do is, see here we have what is the thing, we have the equal number of A's followed by equal number of B's. Okay, and we have a stack. So what we are going to do is that in the stack we have a starting symbol, stack starting symbol Z will be there. So the input file, you will be having your input. Okay, so let us assume that we are taking this as the input. Okay, so the control unit will start read from left to right the input file. So each time, so now this is the top of the stack. Okay, initially this is the top of the stack, and this is the input, first input symbol. The control unit will read, and let us assume that Q0 is the initial state. Okay, so it reads A, and in the top of the stack it reads Z. That is, it means that stack is empty as of now. Okay, so the stack is empty with only the starting symbol of the stack. So we want to now check whether we want to design a push down automata. Okay, we want to design a push down automata that will accept all these strings that belongs to this language. Okay, we want to design a push down automata that will accept all the strings that belongs to this particular language. Okay, so that is our aim to do this particular problem. Okay, we want to give a solution that that will accept all these strings that are present in this language. Okay, so how can we do that? We want to check first when you are reading the number of A's, you can just keep on reading. Okay, that's not an issue. But when B comes, you want to check whether there are equal number of B's as that of A. Okay, so for that what we can do is that whenever you read A, okay, whenever you read A, you just push it into the stack. Okay, as long as you read A, you keep on pushing it into the stack. Okay, and so now when all the A's gets exhausted, okay, so the number of A's may differ, but we have an infinite stack memory, so there is no issue for that. So because n is greater than or equal to 1, that's all. So n can be even 1000 also. Okay, so we do not know n, but we don't have any problem because we have a infinite stack memory. And so as long as you read A, any number of A's, okay, 5, 10, 30, 40, any number of A's that we read, we are just going to push it into the stack. Okay, so after pushing all the A's into the stack, once we start reading the first B, okay, once we start reading the first B, so what we are going to do now, we want to check whether and so what is it actually, for each B there will be a corresponding A. Okay, that is the meaning. So equal number of A's, equal number of B's. So when there is a B, definitely there should be a for that. Okay. So for each B, there should be a corresponding A. Only then we can say that equal number of A's and equal number of B's. So what logic we are going to use is, so whenever you read a B, we are going to check in the top of the stack for a A, and we are going to just push it off, pop it off. Okay, we are going to pop it off. So first what we have done for all A's, okay, we are just going to push it into the stack. So your stack will be now filled with all A's. So now when you start reading B, so for one B, you check whether and corresponding A is available in the stack. Okay, so you check the top of the stack. So while you're reading B, you check the top of the stack whether an A is there. Okay, then you pop it off. Okay, so this will go. So now when you read the second A, then again you go and check the top of the stack. If there is an A, then pop it. Okay, and then coming to the third A, again go and check the top of the stack. There is an A, so pop it. Okay, now the input gets exhausted. Okay, now the input gets exhausted. So now there is nothing. That means lambda, right? So there is no input symbol. So what your transition will take? It will take lambda as the input, correct? So lambda will be taken, and you also now check the top of the stack is also, it becomes empty, okay, because it is having only the starting state, okay, starting symbol. So now at this point we'll be able to say that for each the number of A's and number of B's are equal. Okay, so when you can say that the conditions, okay, the conditions for a string to be accepted in this language. So when you draw a pushdown automata, what is the condition? You can say that a particular string is accepted or not. The first one is the string should be completely read. Okay, string should be read completely, and finally the stack should be empty. So once you read all the, when your input is exhausted, the stack should become empty. Okay, so in this case you can see that as you keep on reading one input from B, okay, so input B, so every time you pop the top of the stack, that is the corresponding A. So after reading all the input, your input, when the input get exhausted, the stack also becomes empty. Okay, so at that point we can say that the given string is accepted by the pushdown automata. Okay, so now let us see how to write the transition functions. So as I have mentioned earlier in the theory part, in the transition function for this pushdown automata, we have three elements on the left hand side. Okay, we have three elements on the left hand side. So that is the current input state and the current input symbol and the symbol on the top of the stack. Okay, so now we will see how to write the transition function for this. So delta of what is the input state, current, the first initial state, we'll take it as Q0. Okay, and let us assume that the input is AA, BB. Okay, so now initially the first input symbol is red. So the current input symbol is A. And at this point, what we'll be having in the stack? The stack starting symbol. Okay, Z. So Q0, comma A, comma Z. Okay, Q0 is the current state or the initial state, and A is the current input symbol that we are reading, and Z is the top of the stack now. Okay, so as we do this, okay, as we have the input symbol is A and the top of the stack is Z, what we are going to do, as we are reading A, we are going to push this A into the stack. Okay, we are going to push this A into the stack. So how will you write that? Now the status, again, we'll keep the status Q naught as long as we read A. Okay, as long as we read A, we'll maintain the status Q naught itself. Okay, and only when we read B, we'll change the state. So now the state remains the same, Q naught. And now what is the content of the stack? Okay, what is that we are going to replace the top of the stack with? Okay, so here what you are going to have is the the string that replaces the top of the stack. Okay, so what we are going to write here is, in the transition function, the string that replaces the top of the stack. Okay, so earlier we have z. Okay, in the top of the stack we have z, and what we are going to replace it with is, we are going to push A into the stack. Okay, so now the content of the stack becomes AZ. Okay, so actually if you are going to push AZ, what happens? You have to do it one by one. Okay, so the we are going to have A in the top of the stack and Z should be in the end. Okay, at the bottom. Okay, so what we are having here is AZ. Okay. So let me rub this, just to make a note of that, the string that replaces the top of the stack. So now, initially we have the top of the stack is Z. Okay. So now again you are going to read the next input symbol. Okay. So while you are reading the next input symbol, actually what we are having, we are reading this input symbol as A. But what is the top of the stack now? The top of the stack is now A. Okay. So the top of the stack is A. And again, what you are going to do, we are going to replace, or we are going to push again A into the stack. Okay. So, okay. So we are going to push A into the stack so that you will be getting AA in your thing. Okay, so next, coming to next step. So this transition will help you to read as many number of A's in your input. Okay, so if, for example, if you have another 2 A's, then what happens? The same transition will keep on working till you read all the A's and push it into the stack. Okay, when you read the third A, again the top of the stack will be A, so you push it into the stack. Again the fourth A. So you keep on pushing into the stack as long as you have A in the input symbol. Okay, in the input. So now once you start reading B, okay, once you start reading B. So for example, delta of the state is now Q naught only, and but the input symbol that you are reading is B. Okay, and currently what is the top of the stack? It is A. Okay, now at this point what we have to do, so for every time you are reading a B, we are going to pop out the symbol from top of the stack. Okay, so as you keep on doing that, for every B, when you pop each A, then finally after reading all the B's, the stack should become empty and the input should also be empty. Okay, so when B is read and when the top of the stack is A, we are going to do the pop operation. So how the pop operation has to be done is using a lambda. So as you know, lambda is an empty string, right? So now we are also changing the state. So once you start reading input B, you change the state to Q1 and the pop operation is represented by the lambda symbol. So what is this? Actually, this is the string that replaces the top of the stack, right? So when you are replacing the top of the stack with lambda, then what it means? This is automatically not there in the stack. Okay, so it is replaced by lambda, an empty string. Okay, so now for the first B, you have done the pop operation. Now, but the state becomes Q1. Okay, now the state becomes Q1. So from state Q1, when you read B, okay, so here until this point, the state was Q0 and you were reading B and the top of the stack was A. And now, since you have started reading B, the state has been changed to Q1 and you have done the pop operation. Now, current state is Q1. Okay, the current state is Q1 and the current input symbol is B and the top of the stack is again A. Okay, so now again what you have to do, you keep on popping out. Okay, so again when you popping out, okay, so it is replaced by this top of the stack is replaced by lambda, that means an empty string, so it goes away. Okay, so this will continue as long as you have B in the input file. Okay, as long as you have any number of B's, you keep on applying this transition and you keep on popping out the top of the stack. So finally at one point what happens, all the B's you have read, okay, and there is no more input. So when there is no more input, what it means, the input, it means that it is lambda. Okay, you have only an empty string lambda, and now at this point the stack should also become empty. Okay, the stack should also will have only the stack starting symbol. Okay, so q1 comma lambda comma z. So if you reach this particular point, okay, the input is exhausted and the stack has become empty, then it means that now the given string is accepted by the thing. Okay, so you are moving to a new final state and having only the leaving the stack with only the stack starting symbol. Okay, so now it means that this q2 is the q2 belongs to the final state, and so any if you are able to follow this for any string that belongs to this language, then all those will be accepted by this pushdown automata. Okay,